Welcome, curious minds. Today we're not just dipping our toes in, we are embarking on a true deep dive. We're looking into the most epic story imaginable, the entire history of the universe. From its mysterious birth, through the fundamental laws that sculpt its very fabric, all the way to its ultimate kind of mind-bending destiny. Our mission today is pretty crystal clear. We've gathered a stack of fascinating sources, groundbreaking cosmological reports, the latest scientific overviews, and we're going to extract the absolute most important nuggets of knowledge for you. Think of it as your express lane to being incredibly well informed about the cosmos, complete with some truly surprising facts you might not have encountered before.
Exactly. We're going to meticulously piece together the evidence-based narrative of our universe's 13.8 billion year journey. Starting right from the theoretical genesis of space-time itself, then moving through the emergence of planetary systems, and ultimately exploring the profound implications of forces like gravity and, well, that enigmatic dark energy. Our focus today will largely center on the prevailing framework in cosmology, the lambda-cold dark matter model, or CDM as it's known, and it's been remarkably successful in explaining the vast majority of astronomical observations we've collected.
Okay, so when we talk about this SCDM model, what are we actually saying the universe is made of? Because it's not quite what you might think, is it?
It's definitely not what most people imagine. The CDM model posits that the universe is composed of three primary constituents, and frankly, two of them are still quite mysterious to us. First, there's baryonic matter. This is the ordinary stuff, everything we can directly see and interact with. Stars, planets, galaxies, the gas clouds between them, and, well, us. But here's the kicker. This familiar matter accounts for only about 5% of the universe's total mass energy content. Just a tiny fraction of the cosmic pie.
Only 5%?
Yeah.
It's astonishing. I mean, just 5%. So what makes up the other 95%?
Well, the next significant component, making up roughly 27% of the universe, is cold dark matter, CDM. This is a non-luminous, basically undetectable substance, and its fundamental nature remains one of the greatest unsolved mysteries in physics. We can't see it, it doesn't interact with light or other electromagnetic radiation in any way that we currently understand. But its gravitational influence is profound. It acts as the primary gravitational scaffolding, the framework that drives cosmic structure formation. It forms an invisible web that pulls in the ordinary matter.
Right, the scaffolding. And then the biggest mystery of all, the dominant component, right?
Precisely. The most dominant component, sitting at approximately 68% of the universe's total mass energy, is dark energy. This enigmatic entity is responsible for something truly weird: the accelerated expansion of the cosmos. Instead of gravity pulling things back together and slowing expansion down, dark energy is actively pushing everything apart, and faster over time. We'll definitely delve deep into each of these throughout our conversation, exploring their distinct and, often surprising roles.
It's incredible how much we've learned, but also, like you said, how much remains unknown. What gives cosmologists such confidence in this particular narrative, this SCDM model, even with these huge unknowns?
That's a fair question. Our confidence isn't speculative, though. It's grounded in multiple independent lines of empirical evidence. These are often referred to as the three primary pillars that robustly corroborate the Big Bang theory. The first is the expansion of the universe. This was Edwin Hubble's groundbreaking observation back in the 1920s. He saw that distant galaxies are systematically receding from us, and the farther away they are, the faster they're moving. This phenomenon, known as Hubble's law, is like, the cosmic equivalent of watching a film in reverse. It directly implies that the universe was once much, much hotter and denser.
And the second pillar, which for me is perhaps one of the most compelling pieces of evidence, is the cosmic microwave background.
CMB?
Discovered accidentally in 1965, right? This faint, uniform thermal radiation permeates all of space. It's the relic afterglow of the Big Bang itself, literally a snapshot of the universe when it was just 380,000 years old and finally became transparent to light. The sheer fact of its existence and its almost perfectly uniform temperature across the sky, that's powerful confirmation of a hot, dense beginning.
It really is. And the third pillar is Big Bang nucleosynthesis, BBN. The Big Bang theory makes incredibly precise predictions about the primordial abundances of the lightest elements. Things like hydrogen, helium, and a tiny bit of lithium, all forged in the first few minutes of the universe's existence. And when astronomers look at the most pristine ancient gas clouds or the oldest stars in the universe, they find these predicted abundances are remarkably consistent with observations. This agreement between theory and observation is an incredibly robust line of support for the Big Bang model.
Okay, let's unpack this incredible story. Imagine, if you can, hitting rewind on the entire universe, all the galaxies, all the stars, everything shrinking, compacting, becoming hotter and denser. Until you reach a point, 13.8 billion years ago, where our most fundamental laws of physics simply break down. This isn't just the beginning of everything, it's the edge of our current understanding. This is where our deep dive truly begins, right in the heart of the Big Bang.
Precisely. This earliest period, from time zero to an unbelievably brief moment, roughly 10 seconds after the Big Bang, is what cosmologists call the Planck epoch. During this fleeting instant, the conditions were so extreme, unimaginable density, unimaginable temperature, that all four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, are hypothesized to have been unified into a single, all-encompassing superforce. Our current understanding of physics, even Einstein's general theory of relativity, simply doesn't apply here. It breaks down. A complete description of the Planck epoch truly awaits the development of a successful theory of quantum gravity, one that can finally unify general relativity with quantum mechanics.
Okay, here's where it gets really interesting and frankly a bit mind-bending. Following those initial incomprehensible moments, the universe supposedly underwent a stupendous faster-than-light expansion. It's known as cosmic inflation. This sounds like something out of science fiction, but it's actually, well, an ingenious solution to some fundamental problems with the standard Big Bang theory.
That's right. Proposed by physicist Alan Guth in the 1980s, this hypothesis suggests that in a tiny fraction of a second, we're talking from roughly 10 arcseconds after the Big Bang, space itself expanded exponentially. To put it into perspective, a region of space smaller than an atom would have inflated to a size larger than our entire observable universe today. And crucially, this wasn't matter moving through space, mind you, but the very fabric of space-time itself expanding at this incredible rate. It was powered by the energy of a hypothetical field called the inflaton field.
And this rapid expansion wasn't just some dramatic cosmic event. It was the elegant answer to some of the Big Bang's biggest head-scratchers, right?
Exactly. It solved what's known as the horizon problem. You see, when we look at the cosmic microwave background, it shows remarkably uniform temperatures across vast distances, even in regions that, according to the standard Big Bang without inflation, shouldn't have been in causal contact, meaning light and information couldn't have traveled between them since the Big Bang to even out the temperature. Inflation resolves this beautifully by positing that these regions were once in causal contact, compressed into a much smaller pre-inflationary universe. They had time to reach thermal equilibrium before being stretched incredibly far apart by inflation, thus preserving their uniform temperature. And it also elegantly addressed the flatness problem. Observations indicate our universe is incredibly close to being perfectly flat, geometrically speaking. For this to be true today, the early universe needed to be flat to an extraordinary degree of precision. It's like balancing a pencil on its point for billions of years. Inflation provides a natural explanation. Any initial curvature of space-time, whether positive like a sphere or negative like a saddle, would have been stretched out to near-perfect flatness during the exponential expansion. Much like inflating a crumpled balloon makes its surface appear smooth and flat to an ant living on it.
Okay, but perhaps the most profound consequence of inflation, though, is how it essentially seeded all the large-scale structures we see in the cosmos today. That's truly mind-bending. Where did the seeds come from?
It truly is profound. At the microscopic level, quantum mechanics dictates that space-time isn't perfectly smooth. It's more like a quantum foam, with tiny spontaneous fluctuations in energy and density constantly popping in and out of existence, governed by the Heisenberg uncertainty principle. Before inflation, when the universe was of subatomic size, these quantum fluctuations were a dominant feature. Then, the immense rapid stretching of spacetime during inflation took these microscopic subatomic quantum jitters and magnified them, stretched them out to macroscopic and then astronomical scales. So what happened was that regions that were infinitesimally denser due to a random quantum fluctuation were stretched into vast overdensities. Similarly, less dense regions were stretched into vast underdensities. These minute density variations, imprinted on the fabric of the cosmos in its very first moments, became the primordial seeds for all future structure formation galaxies, clusters of galaxies, the whole cosmic web. This establishes a direct and remarkable causal chain from the probabilistic nature of the quantum world to the grand deterministic architecture of the universe we observe. The largest structures in the cosmos are, in a very real sense, fossilized relics of quantum events from the first tiny fraction of a second of time.
Wow. And then, after this explosive growth spurt, the inflationary epoch had a sudden mysterious end. And that marked the transition into the hot Big Bang phase we usually imagine.
Yes, exactly. In a process called reheating, the immense potential energy stored in that inflaton field didn't just vanish, it decayed. It flooded the universe with a hot, dense, and remarkably uniform soup of fundamental particles, quarks, electrons, photons, and radiation. This event truly marks the beginning of the hot Big Bang phase proper, setting the stage for the sequence of elements that would rapidly forge the very first matter. So following this reheating phase, the universe was this unimaginably hot and dense plasma. But as it continued to expand, it also cooled very rapidly. This cooling triggered a series of what we call phase transitions, which are kind of like steam condensing into water or water freezing into ice, but on a fundamental physics level. During these transitions, the fundamental forces of nature separated from one another, and the elementary particles that constitute our universe began to emerge in a precise chronological sequence. Right after the Planck epoch, we entered what's conceptually known as the Grand Unification epoch. During this unbelievably brief period, gravity is believed to have frozen out or separated from the other three forces, the strong, weak, and electromagnetic forces, which were still unified as a single GUT force. Moving quickly through those earliest moments, as the universe kept cooling, it triggered more of these fundamental phase transitions. Each time, a new fundamental force, like the strong nuclear force, would break away from the others. It was a chaotic but critically important period of particle emergence. For instance, it was during the electroweak epoch, lasting until about 10 seconds, that fundamental particles like quarks and electrons actually acquired their mass. This happened thanks to their interaction with the Higgs field, as the electromagnetic and weak forces finally separated. Before this, everything was massless. Then we entered the quark epoch. With all four fundamental forces now distinct, the universe was a seething hot plasma of quarks, leptons like electrons and neutrinos and their corresponding antiparticles. But here's the absolute cosmic miracle, something we call baryogenesis. In that super hot, dense soup, particles and antiparticles were constantly being created and annihilated. But for reasons we're still trying to fully grasp, there was a tiny asymmetry. For every billion particles of antimatter that plopped into existence and then annihilated with a matter particle, there was, astonishingly, just one extra matter particle left over.
Just 1 in a billion.
1 in a billion. Think about that. This tiny fundamental imbalance is the only reason there's anything left today. Stars, planets, us. Without it, the universe would be pure energy, pure radiation, no solid stuff at all. It's truly a cosmic asymmetry that led to everything. Following that, as the universe cooled further, below about 10 Kelvin, we entered the Hadron epoch. The strong nuclear force became powerful enough to bind quarks together into composite particles called hadrons. This process, known as quark confinement, led to the formation of the first protons and neutrons, the building blocks of atomic nuclei. Any remaining matter-antimatter pairs, like protons and antiprotons, annihilated each other, leaving behind that slight excess of protons and neutrons that would eventually form all future atoms. And finally, in this very early sequence, we move into the lepton epoch, from about 1 second to 3 minutes. After the majority of hadrons and antihadrons annihilated, the universe's mass was dominated by leptons, electrons, neutrinos, and their antiparticles, positrons. As the temperature continued to fall below 10 Kelvin, most electron-positron pairs also annihilated each other, releasing their energy as photons. This left behind a small residual number of electrons, precisely enough to balance the positive charge of the protons, ensuring the universe would eventually become electrically neutral. It was also during this epoch that neutrinos essentially decoupled from other matter. They stopped interacting significantly, forming a cosmic neutrino background that, while theoretically present, is incredibly difficult to detect today.
So by a mere 3 minutes after the Big Bang, the universe had cooled to about 1 billion Kelvin, which is like the core of a massive star. And for a brief period, maybe 17 minutes or so, the entire cosmos transformed into a nuclear furnace.
Exactly. This was Big Bang nucleosynthesis, BBN, the process that forged the very first atomic nuclei heavier than hydrogen. The primary product, the most stable of the light nuclei formed, was helium-4, composed of 2 protons and 2 neutrons. But the formation of helium-4 couldn't happen immediately. It required an intermediate step, the creation of deuterium, which is a nucleus with just 1 proton and 1 neutron, an isotope of hydrogen. For the first few minutes, the universe was simply too hot and dense. Any deuterium nucleus that formed was immediately blasted apart by high-energy photons before it could fuse further. This phenomenon, known as the deuterium bottleneck, effectively delayed the main phase of nucleosynthesis until the universe had cooled sufficiently, below about 10 Kelvin, for deuterium to survive long enough to fuse into heavier elements.
Okay, so once that temperature dropped below 1 billion Kelvin, the bottleneck broke, and it was basically game on for cosmic element creation.
Spot on. This triggered a rapid and incredibly efficient burst of nuclear reactions. Essentially, all of the free neutrons that had survived from the earlier epochs, which at this point were outnumbered by protons by about 7-to-1 due to neutron decay, were rapidly incorporated into helium-4 nuclei. And the theory of BBN is a cornerstone of modern cosmology, precisely because it makes highly specific, testable predictions based on well-understood nuclear physics from laboratory experiments. Given just one single cosmological parameter, the ratio of baryons, protons and neutrons to photons, BBN predicts the primordial mass abundances, roughly 75% hydrogen-1 protons, about 25% helium-4, and trace amounts of deuterium, about the 0.01%, helium-3, and lithium-7, maybe 1 part in 10 billion. This predictive power is immense. If observed abundances didn't align with these predictions, the Big Bang theory would be in serious trouble. But astronomers, when they measure these abundances in the most ancient environments we can find, like distant quasar absorption systems or very old metal-poor stars in our own galaxy's halo, find stunning agreement with the BBN predictions. What's more, the value for the baryon to photon ratio derived from BBN independently matches the value derived from analyzing the tiny fluctuations in the cosmic microwave background. This incredible consistency across two completely different physical regimes and cosmic epochs, nuclear physics in the first few minutes and plasma physics at 380,000 years, provides overwhelming evidence for the validity of the standard cosmological model.
So after about 20 minutes, the cosmic furnace cooled and expanded enough that the density dropped, and BBN essentially ceased. The universe was left with its primordial composition, a relatively simple blend of roughly 3/4 hydrogen and 1/4 helium by mass.
That's right. And importantly, BBN didn't produce any elements heavier than lithium in significant amounts. This is due to obstacles in nuclear physics, particularly what's called a mass 8 gap. There's no stable nucleus with a mass number of 5 or 8. This means you can't easily add a proton or neutron to a helium-4 nucleus to make a stable isotope. And fusing two helium-4 nuclei, which would have mass 8, doesn't readily form a stable product in those conditions. In modern stars, this gap is bypassed by a slower process called the triple alpha process to form carbon, but this requires the very high densities and long timescales found in stellar cores conditions that simply weren't met in the rapidly expanding and cooling early universe. So all the elements heavier than lithium, everything from the carbon in our bodies, the oxygen we breathe, the silicon in rocks and computers, the iron in our blood, the gold in jewelry, all of that had to be forged much later, inside stars and during violent stellar events like supernovae.
Okay, so fast forward a bit. For the first 380,000 years, the universe was an opaque, incandescent fog. You couldn't see through it at all. It was literally a thick, hot, dense plasma of protons, helium nuclei, and crucially, free electrons zipping around.
That's exactly right. Photons, the particles of light, were essentially trapped. They were constantly scattering off those free electrons in a process known as Thomson scattering. Any photon emitted would bump into an electron almost immediately, changing its direction. Light couldn't travel freely across space. Imagine being inside a dense, brilliant cloud where light is just bouncing around everywhere like pinballs. You'd be effectively blind to anything outside your immediate vicinity.
This opaque state continued until the universe expanded and cooled to a critical temperature of about 3,000 Kelvin. What happened then? What changed?
At this temperature, the average energy of the photons dropped below the energy required to knock an electron off a hydrogen atom, the ionization energy. As a result, electrons were finally captured by the protons and helium nuclei, combining to form stable, electrically neutral atoms. This pivotal event is known as the epoch of recombination. Though it's a bit of a misnomer, actually, because the electrons and nuclei had never actually been combined before this point. They were always kept separate by the extreme heat. So maybe combination would be a better term. With the electrons now safely bound within neutral atoms, the primary obstacle for photons, those free-roaming electrons, vanished. The photons decoupled from matter. The cosmic fog lifted. For the first time in its history, the universe became transparent, allowing photons to stream freely across the cosmos, unimpeded, on journeys that would last for billions of years.
And these photons, the light unleashed at decoupling, 380,000 years after the Big Bang, are still detectable today.
That's truly amazing, like looking at the universe's actual baby picture. They are indeed. These relic photons have been traveling through the expanding universe for the subsequent 13.8 billion years. As space itself has expanded during that time, their wavelengths have been stretched enormously by a factor of approximately 1100. This cosmological redshift has shifted the light from its original high-energy state, mostly visible in infrared light, into the low-energy microwave portion of the electromagnetic spectrum. This ancient light is what we now detect as the cosmic microwave background, CMB. It was discovered, really quite accidentally, in 1965 by Arno Penzias and Robert Wilson at Bell Labs, who were trying to eliminate noise in a microwave receiver. They were awarded the Nobel Prize for their finding. Subsequent, increasingly precise measurements by space-based observatories like NASA's COBE, WMETS, and the European Space Agency's Planck satellite have confirmed its near-perfect black body thermal spectrum, with a current average temperature of 2.725 Kelvin, just a few degrees above absolute zero. Now, while the CMB is remarkably uniform in temperature across the entire sky, these advanced satellites were sensitive enough to detect minute temperature fluctuations, or anisotropies. We're talking differences on the order of just 1 part in 100,000. These are not random noise, they are incredibly important. They are a direct snapshot of those primordial density fluctuations, the very seeds planted by cosmic inflation, at the precise moment the universe became transparent. Regions that were slightly denser back then were slightly hotter, red spots in the CMB maps, and regions that were slightly less dense were slightly cooler, blue spots. This baby picture of the universe is arguably the single most important source of data in modern cosmology. The statistical properties of these tiny temperature variations hold the blueprints for all the large-scale structure, galaxies, clusters, voids that would later form.
So the universe had its baby picture taken in the CMB, and then nothing. It plunged into what sounds like a truly silent, featureless epoch. Tell us about this period, the cosmic dark ages, and what was actually happening in the apparent void.
That's a perfect way to put it. Yes, after the CMB's release, the brilliant light of the Big Bang had faded, red-shifted into the microwave spectrum, and there were not yet any stars or galaxies formed to illuminate the cosmos. The universe entered a long, quiet period, often called the Cosmic Dark Ages. This lasted from roughly 380,000 years after the Big Bang until the first stars began to ignite, maybe around 100 to 200 million years later. During this time, the universe was filled with vast, dark clouds of electrically neutral hydrogen and helium gas. But it wasn't completely static. Silently and slowly, this gas began to respond to the subtle gravitational pull of the density fluctuations that were imprinted on the fabric of space-time back during inflation and revealed in the CMB. This was the calm before the storm of structure formation, a truly unseen chapter where the foundations for everything we see today were quietly being laid down by gravity.
Okay, so it sounds like the universe couldn't have possibly transitioned from the near-perfect smoothness we see in the CMB to the incredibly complex galaxy-rich tapestry we observe today with only ordinary matter. The story of structure formation seems dominated by this invisible protagonist, dark matter. It's almost like a cosmic stage manager working behind the scenes, setting everything up.
That's a fantastic analogy. Yes, the existence of dark matter was first inferred from a profound discrepancy, a mismatch between the amount of visible mass we could see in galaxies and galaxy clusters and the much larger amount of gravitational mass needed to explain the motions of objects within them. This problem of missing mass has been a central mystery in astronomy for decades now. In the 1970s, pioneering work by astronomer Vera Rubin provided really compelling evidence. She carefully measured the speeds of stars orbiting in the outer regions of spiral galaxies. Newtonian gravity predicted they should slow down significantly the farther out they were from the bright galactic center, just like the outer planets in our solar system orbit slower than the inner ones. But she observed flat rotation curves where orbital speed remains constant or even increases with distance. This strongly implied the presence of a much larger invisible halo of matter surrounding the visible galaxy, providing the extra gravitational pull needed to keep those outer stars moving so fast. And even decades earlier, back in the 1930s, astronomer Fritz Zwicky was studying the Coma cluster of galaxies. He noticed that the individual galaxies within the cluster were moving far too rapidly to be gravitationally bound just by the mass of the stars and gas he could see. He postulated the existence of Dunkelmaterie, German for dark matter, to account for the discrepancy. His ideas were largely ignored at the time, but they were remarkably prescient. This was later powerfully reinforced by observations of gravitational lensing. We see that massive foreground objects, like galaxy clusters, bend the light from more distant objects behind them, acting like a cosmic magnifying glass. The amount of bending, the degree of lensing, consistently reveals far more mass than is visible in stars and gas, indicating the dominant presence of unseen dark matter. What's truly fascinating, and perhaps the most direct observational evidence we have for dark matter behaving differently from ordinary matter, is the Bullet Cluster. This is a spectacular collision of two galaxy clusters. Gravitational lensing maps of this collision show that the bulk of the mass, which is the dark matter, passed right through the collision almost unimpeded, like ghosts. Meanwhile, the hot baryonic gas, the ordinary matter, which is visible in X-ray telescopes, was slowed down and significantly displaced by the collision, like a shock wave. This provides direct proof that most of the gravitational mass in these systems is not in the form of ordinary interacting matter, but something else entirely that doesn't interact except through gravity.
So based on all these different lines of evidence, rotation curves, cluster dynamics, lensing, the bullet cluster dark matter is understood to constitute about 27% of the universe's total mass energy content. That's over 5 times more than all the ordinary matter combined. But what is it? And why is it so crucial that it's cold dark matter?
Indeed, 27%. And its defining characteristic is that it doesn't interact with light or any other form of electromagnetic radiation in any significant way, making it completely invisible to all our telescopes. Its fundamental nature remains one of the greatest unsolved mysteries in physics. The leading candidates are hypothetical, as yet undiscovered elementary particles, perhaps something like WIMPs, weakly interacting massive particles, or possibly axions. There are active experiments underway trying to detect these particles directly or indirectly. Crucially, for cosmological models, it needs to be cold, as in cold dark matter, CDM. This means its constituent particles were moving slowly, much slower than the speed of light in the early universe. This cold property is essential for the hierarchical or bottom-up model of structure formation that observations strongly support. It allows smaller clumps of dark matter to form first and then gravitationally merge over time to build larger structures like galaxies and clusters. If dark matter were hot, moving near light speed, it would have smoothed out small-scale density fluctuations, preventing the formation of small structures first. Remember, the initial density fluctuations in baryonic matter, the ordinary stuff seen in the CMB, were tiny, only about 1 part in 100,000. Cosmological simulations running on supercomputers consistently demonstrate that gravity acting on these tiny baryonic fluctuations alone is simply too weak to form the complex structures we see today within the 13.8 billion years the universe has existed. The universe would still be almost perfectly smooth. Dark matter provides the essential solution to this timing problem. Because dark matter doesn't interact with photons, it wasn't subject to the intense radiation pressure that prevented baryonic matter from clumping together effectively in the hot, dense, opaque early universe. Dark matter was therefore free to begin the process of gravitational collapse much earlier. It started to coalesce within those primordial density fluctuations as soon as the universe became matter-dominated, around 50,000 years after the Big Bang. It essentially gave structure formation a crucial 300,000-year head start compared to ordinary matter. This early collapse led to the formation of gravitationally bound dark matter halos of various sizes, which then acted as the essential gravitational scaffolding, or wells, into which ordinary matter could later fall to form galaxies.
So it sounds like without this invisible scaffolding of dark matter, the universe would still be, well, pretty much a formless soup. Is it fair to say dark matter is the unsung hero of cosmic structure? Almost more important, gravitationally speaking, than the stuff we can actually see.
It's absolutely fair to say that. Dark matter is, in essence, the gravitational architect of the large-scale universe. Over hundreds of millions and billions of years, gravitational instability amplified these initial dark matter structures. Large-scale N-body computer simulations, which model the gravitational evolution of millions or billions of dark matter particles, show that this growth naturally forms a vast, intricate, and interconnected network of structures known throughout cosmology as the cosmic web. This web consists of dense, long filaments and vast, planar sheets of dark matter surrounding enormous, relatively empty regions called voids. The densest points in this cosmic network are the nodes where multiple filaments intersect, and it is within these high-density nodes that the most massive galaxy clusters eventually form. And this characteristic web-like structure, predicted by simulations based on the SEDM model, has been spectacularly confirmed by large-scale galaxy surveys, like the Sloan Digital Sky Survey, or DSI. These surveys map the three-dimensional positions of millions of galaxies, revealing that they are not distributed randomly throughout space, but clearly trace this underlying invisible dark matter skeleton. Galaxies essentially light up the cosmic web.
Okay, so this invisible scaffolding of dark matter halos set the stage for the next dramatic act. The universe finally lighting up, marking the end of the Dark Ages and the beginning of the cosmic dawn. What did those first moments of light actually look like?
It was truly a cosmic awakening after hundreds of millions of years of darkness. After the universe became transparent at the epoch of recombination, the now neutral hydrogen and helium gas was free to respond fully to gravity. This primordial gas began to stream along the filaments of the cosmic web and fall into the deep gravitational potential wells created by the pre-existing dark matter halos. As these pristine gas clouds were pulled into the centers of the densest, earliest forming dark matter halos, they were compressed, becoming denser and hotter. Eventually, in the very cores of these collapsing clouds, the temperature and pressure reached the critical threshold of millions of Kelvin required to ignite nuclear fusion. This ignited the very first stars, an event believed to have occurred somewhere between 100 and 200 million years after the Big Bang. These first-generation stars, which astronomers designate as population 3 stars, are thought to have been fundamentally different from the stars we see forming today, like our Sun, which is a population I star. Because they were forged from pure hydrogen and helium gas left over from the Big Bang, they completely lacked the heavier elements, what astronomers collectively call metals, that act as efficient coolants in modern star-forming gas clouds. The absence of these coolants meant the gas couldn't cool and fragment as easily, leading to the formation of extraordinarily massive stars, perhaps 30 to 300 times the mass of our Sun. These behemoths would also have been incredibly hot and luminous, shining millions of times brighter than the Sun, with surface temperatures perhaps exceeding 100,000 Kelvin. But due to their extreme mass, they would have burned through their nuclear fuel at a furious rate and had very short lifespans, likely only a few million years, compared to the Sun's 10 billion year lifespan. And these population third stars likely didn't form in isolation. They probably formed in small groups or clusters within the smallest dark matter halos that collapsed first. These clusters of first stars effectively became the nuclei of the very first protogalaxies. The prevailing model of galaxy formation, as we mentioned, is hierarchical or bottom-up. This means that these small initial protogalaxies, seeded by the first stars, grew over cosmic time by repeatedly merging with one another, gradually building up into the larger, more structured galaxies like our own Milky Way that dominate the universe today.
Right. And the birth of these first monster stars had a profound universe-wide impact, didn't they? It sounds like they basically flipped a switch for the entire universe, changing its state.
They absolutely did. Their incredibly intense, high-energy ultraviolet radiation began to pour out into the surrounding neutral hydrogen gas that filled the vast intergalactic medium between these early protogalaxies. This energetic radiation had enough energy to strip the electrons from the neutral hydrogen atoms, ionizing them once again. This process, occurring on a cosmic scale, is known as cosmic reionization. It effectively reversed the process of recombination that had happened hundreds of thousands of years earlier. Over several 100 million years, the bubbles of ionized gas around the growing populations of first stars and early galaxies expanded and merged until by about 1 billion years after the Big Bang, nearly all the hydrogen in the intergalactic medium was once again an ionized plasma. This made the universe transparent again, this time not just to visible light and microwaves, but also to ultraviolet light. And the final, absolutely crucial contribution of these first stars was to begin the process of cosmic chemical enrichment. When these massive population 3 stars exhausted their nuclear fuel after just a few million years, they died in cataclysmic supernova explosions, or possibly collapsed directly into black holes. Those that exploded as supernova forged elements heavier than hydrogen and helium, the first metals like carbon, oxygen, silicon, iron, and many others, in their fiery cores during their lives and in the explosion itself. They then ejected these newly synthesized heavy elements into the surrounding interstellar gas. This seeding of the cosmos with the first metals was a critical turning point in cosmic evolution. These heavy elements were incorporated into the next generation of stars known as population 2 stars, which are metal poor compared to the Sun. More importantly, their presence enabled the formation of dust grains, which are essential coolants for later star formation and are the fundamental building blocks for the formation of planets and, ultimately, life as we know it. Without these first stars polluting the universe, we wouldn't be here.
So the death of those first stars, those population Earth through giants, gave the universe the essential ingredients for rocky planets and even life itself. Okay, now let's bring it closer to home. How do stars, like our own Sun and their accompanying planetary systems, actually come to be formed from this enriched gas and dust?
Right. Modern star formation, the kind happening now in galaxies like the Milky Way, typically takes place within giant molecular clouds, GMCs. These are vast, cold, just 10-20 Kelvin above absolute zero, and dense agglomerations of molecular hydrogen gas and interstellar dust grains that can span hundreds of light years and contain enough material to form thousands or even millions of stars. Within these clouds, gravity is the master architect. While gas pressure and magnetic fields provide some support against collapse, gravity eventually wins out in the densest regions, or cores, causing them to contract and collapse under their own weight. This gravitational collapse is the fundamental trigger for the birth of a new star, or a cluster of stars. As one of these dense cores collapses, the material at its center is compressed and heats up significantly due to the conversion of gravitational potential energy into thermal energy. This forms a hot, dense object known as a protostar, the embryonic stage of a star. This protostar continues to grow in mass by accreting gas and dust from its surrounding collapsing envelope. However, as the cloud collapses, any slight initial rotation it possessed is amplified due to the conservation of angular momentum. Think of an ice skater spinning faster as she pulls her arms in. This rotation prevents all the infalling material from falling directly onto the protostar. Instead, a significant fraction of it settles into a flattened, spinning disk of gas and dust orbiting the central protostar. This is known as a protoplanetary disk, or sometimes a circumstellar disk. The formation of this disk is not an incidental detail. It seems to be a ubiquitous and essential part of the star formation process. And crucially, it is within these swirling disks that planets are born. Planets appear to be a natural, perhaps even inevitable, byproduct of making a star.
Okay, so we have the spinning disk of gas and dust around a baby star. How do we get from that swirling mixture to actual solid planets? It sounds like an almost impossible leap going from microscopic dust to something Earth-sized.
The process is generally understood to be accretion, and it's a hierarchical, bottom-up process that unfolds over millions of years within the protoplanetary disk. It begins with microscopic dust grains composed of those heavier elements like silicates, rock, and carbonaceous compounds, sometimes coated with ice depending on the location in the disk sticking together. Initially, the sticking might be due to electrostatic forces or sticky organic coatings. As these aggregates grow from dust bunnies to pebbles, then to rocks, and eventually to boulder-sized objects, their own gravity starts to become significant, allowing them to attract more material gravitationally. This collisional growth continues until the disk is populated with numerous kilometer-sized bodies called planetesimals. These are considered the fundamental building blocks of planets. These planetesimals orbit the young star within the disk, and their paths frequently cross, leading to collisions. Some collisions might be destructive, but others lead to mergers. Through a process often called runaway growth, the largest planetesimals in a given region having the strongest gravitational pull grow the fastest. They gravitationally dominate their local neighborhood, sweeping up smaller planetesimals and debris more efficiently. Over longer timescales, perhaps millions to tens of millions of years, a related process called oligarchic growth takes over, where a few large oligarchs dominate accretion in their feeding zones. Eventually, this process of mergers and gravitational accretion clears out distinct orbital paths around the star, leading to the formation of a small number of large, gravitationally dominant bodies, the planets. Now, a key factor determining the type of planet that forms is its distance from the central star. This relationship is often characterized by the location of the frost line, or snow line, within the protoplanetary disk. The frost line is the radius beyond which it is cold enough for volatile compounds, primarily water, but also others like ammonia and methane CH, to condense from gas into solid ice grains. Inside the frost line, closer to the young, hot star, temperatures are too high for these ices to form or survive. Only refractory materials with high condensation temperatures, like rock silicates, and metal, primarily iron, can exist as solids. This significantly limits the total amount of solid material available for planet building in the inner disk. Consequently, the planets that form here tend to be smaller, denser terrestrial planets composed mainly of rock and metal, like Mercury, Venus, Earth, and Mars in our solar system. The formation of these rocky worlds is thought to be a relatively slow process, perhaps taking tens of millions of years to fully assemble. Beyond the frost line, however, the situation is dramatically different. In addition to rock and metal dust grains, the vast quantities of water and other volatile compounds present in the protoplanetary disk, water is very abundant in the cosmos, can condense into solid ice particles. This hugely increases, perhaps by a factor of 10 or more, the total amount of solid material available for building planetary cores. Planetary cores forming in this outer region can therefore grow much larger and much more quickly than their inner system counterparts. Once a solid core reaches a critical mass, estimated to be around 10 Earth masses, its gravity becomes powerful enough to rapidly capture and hold on to the most abundant elements in the entire disk: hydrogen and helium gas. This phase of rapid gas accretion builds the colossal atmospheres of the gas giants like Jupiter and Saturn, and the somewhat smaller but still huge ice giants like Uranus and Neptune, which likely accreted less gas or formed later. This entire process of forming giant planets is thought to happen very quickly, likely within the first few million, perhaps up to 10 million years of the solar system's life, before the young star's strong stellar wind and radiation pressure blow away the remaining primordial gas in the disk.
And this overall model successfully explains the fundamental architecture of our own solar system, doesn't it? Our system began to form about 4.6 billion years ago. That's roughly 9.2 billion years after the Big Bang, coalescing from a cloud of gas and dust enriched by the remnants of previous stellar generations. We saw the sun's birth at the center, the rapid formation of the gas giants beyond the frost line, the slower assembly of our interterrestrial planets, and likely a subsequent period of intense bombardment as the final planets gravitationally cleared their orbits of leftover planetesimals and debris. A particularly significant event in our early history, we think, was a giant impact on the young Earth, which likely led to the formation of our moon. Okay, let's pivot now. We've talked about the stuff of the universe and how it forms structures. Now let's talk about the silent conductor of this whole cosmic orchestra, gravity. Our understanding of this fundamental force has undergone a profound transformation, hasn't it? Moving from the classical mechanics of Isaac Newton to the, geometric reality of Albert Einstein.
Absolutely. It's a fantastic story in the history of science. In 1687, Sir Isaac Newton published his monumental work, Philosophiae Naturalis Principia Mathematica. In it, he laid out his law of universal gravitation. This was a truly revolutionary achievement. It represented what we can rightly call the first great unification in physics. Newton showed mathematically that the very same force responsible for an apple falling from a tree on Earth was also the force that kept the moon in its orbit around the Earth and kept the planets in their stately dance around the sun. He unified the terrestrial realm with the celestial realm under one simple law. And Newton's law is renowned for its elegance and simplicity. It states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and, crucially, inversely proportional to the square of the distance between their centers. This is the iconic F-G-Area equation that many learn in school. G here is the universal gravitational constant, a fundamental constant of nature, which was first measured with reasonable precision by Henry Cavendish in a famous experiment in 1798. Newton's law provided an incredibly powerful and predictive mathematical framework for understanding the workings of the solar system and beyond, at least on scales accessible at the time. It successfully explained a vast range of phenomena with remarkable accuracy, including the elliptical orbits of planets that Johannes Kepler had described empirically decades earlier, the cause of ocean tides due to the moon's and sun's gravity, and the acceleration of falling objects near Earth's surface. It also clarified the crucial conceptual distinction between mass, which is an intrinsic property of an object representing its quantity of matter or inertia, and weight, which is the gravitational force exerted on that mass by a celestial body like the Earth. An object's mass is constant wherever it is, but its weight can change depending on the strength of the local gravitational field.
So for centuries, Newton's law reigned supreme. It seemed like he had everything figured out regarding gravity. Why wasn't it the final word? What were its limitations?
Despite its incredible success and longevity, Newton's law is ultimately an approximation, albeit an extremely good one in most everyday situations. It operated within a specific conceptual framework that we now know is incomplete. Newton conceived of gravity acting within an absolute space and an absolute time, a static, unchanging, three-dimensional Euclidean stage, and a universally flowing independent time, the same for all observers. Within this framework, gravity was described as an instantaneous action at a distance, meaning the gravitational effect of, say, the sun on the Earth was thought to be transmitted instantly across space, regardless of the distance. Newton himself found this idea philosophically troubling, but the maths worked. However, Newton's theory began to show cracks, very subtle ones, in specific extreme regimes, in very strong gravitational fields, or for objects moving at speeds approaching the speed of light. Most famously, it couldn't perfectly account for a small but persistent anomaly in the orbit of the planet Mercury. Its perihelion, the point in its orbit where it's closest to the sun, advances or precesses slightly faster each century than predicted by Newtonian physics, even after accounting for the gravitational tugs of all the other planets. Resolving this and other conceptual issues, like its incompatibility with Einstein's theory of special relativity, required a complete reconceptualization of gravity itself.
Right, and that reconceptualization came from Albert Einstein. This raises the crucial question. What was Einstein's big idea that so completely changed how we understand gravity? What fundamental shift did he introduce with general relativity?
In 1915, Albert Einstein published his general theory of relativity, presenting a new theory of gravity that was not just a refinement of Newton's law, but a complete paradigm shift. It was revolutionary. In Einstein's view, gravity isn't a force that propagates through space from one object to another, like magnetism. Instead, gravity is a manifestation of the curvature of space-time itself. Mass and energy, according to Einstein, don't exert a pull in the Newtonian sense. Instead, they fundamentally warp, or curve, the very fabric of reality, the four-dimensional combination of space and time. The central tenet of the theory is perhaps most elegantly summarized by the physicist John Wheeler. Space-time tells matter how to move, matter tells space-time how to curve. It's a dynamic interplay. The conceptual starting point for general relativity, Einstein's initial insight, was the equivalence principle. He realized through a famous thought experiment that the effects of gravity are locally indistinguishable from the effects of acceleration. Imagine an observer in a closed, windowless elevator cabin out in deep space, far from any significant gravitational sources. If that elevator starts accelerating upwards at 9.8 meters per second squared, equal to Earth's surface gravity, the observer inside would feel the exact same force pressing them to the floor as an observer standing still on the surface of the Earth. They couldn't tell the difference locally. Conversely, an observer in an elevator whose cable has snapped and is in free fall towards Earth would feel perfectly weightless, just like an astronaut floating in space. This equivalence led Einstein to conclude that gravity is not a true force in the Newtonian sense, but rather a fictitious force, like the centrifugal force you feel in a spinning car that arises from observing the world from a particular reference frame, in this case from within a curved spacetime. This insight leads to a radical new picture of motion under gravity. In general relativity, objects moving under the influence of what we perceive as gravity, say, a planet orbiting the sun, or a beam of light passing near a massive star, are not actually being deflected by a force pulling on them. Instead, they are simply following the straightest possible path available to them through a curved four-dimensional spacetime. This straightest possible path in curved spacetime is called a geodesic. So, the sun doesn't pull on the Earth with an invisible string. Instead, the sun's immense mass warps the space-time geometry around it, and the Earth follows a geodesic, the straightest path it can in this warped geometry, which, from our three-dimensional perspective, happens to look like an elliptical orbit. The common analogy of a bowling ball on a stretched rubber sheet is helpful to visualize warping, but it can be misleading because it still implicitly uses Earth's gravity, pulling the bowling ball down, to explain gravity. A better, though harder to visualize, concept is intrinsic curvature. Imagine two-dimensional beings living on the surface of a sphere. They could determine their world is intrinsically curved without reference to a third dimension by, for instance, drawing a large triangle and finding that the sum of its angles is more than 180 degrees. Similarly, our four-dimensional spacetime has an intrinsic curvature caused by mass and energy. Another powerful and experimentally verified way to intuit this curvature is through gravitational time dilation. General relativity predicts that time itself runs slower in stronger gravitational fields, meaning clocks tick slower closer to a massive object compared to clocks farther away. This effect, while tiny in everyday life, has been measured with high precision using atomic clocks and is a necessary correction for technologies like the Global Positioning System, GPS, to function accurately. An object in a stable orbit, like the Earth around the Sun, is, in a very real sense, following a path through spacetime that maximizes its own proper time, the time measured by its own clock. This drive to follow a path of extremal time through a spacetime where the rate of time's passage varies from point to point is fundamentally what we perceive as the force of gravity. And crucially, general relativity is not just a philosophical proposition or a mathematical curiosity. It is a robust scientific theory that makes precise, falsifiable predictions about the behavior of gravity, many of which were radically different from Newtonian predictions. And it stands today as one of the most rigorously tested theories in all of science. Most immediately, it precisely accounted for the anomalous precession of Mercury's orbit, the very problem that Newtonian gravity could not fully explain. This was a major early triumph for the theory. Einstein also predicted that the path of light itself would be bent as it passed near massive objects due to the warping of spacetime. This was famously confirmed by expeditions led by Sir Arthur Eddington during a total solar eclipse in 1919, which observed the apparent shift in the positions of stars near the sun's limb. Today, gravitational lensing is a vital observational tool in modern astronomy, used for mapping the distribution of dark matter, magnifying distant galaxies, and even finding exoplanets. Furthermore, Einstein predicted that accelerating massive objects, such as pairs of orbiting black holes or neutron stars, would create ripples or disturbances in the fabric of spacetime itself, propagating outwards at the speed of light. These are gravitational waves. These incredibly faint ripples were directly detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory LIGO collaboration, resulting from the merger of two black holes over 1 billion light-years away. This opened an entirely new window gravitational wave astronomy to observe the most violent events in the universe. And finally, the mathematical equations of general relativity permit solutions that describe regions of spacetime so intensely curved by mass or energy that nothing, not even light, can escape once it crosses a boundary called the event horizon. These are black holes. While initially controversial, there is now overwhelming astrophysical evidence for the existence of these objects, ranging from stellar mass black holes formed from the collapse of massive stars to the supermassive black holes, millions or billions of times the sun's mass, that are found at the centers of nearly all large galaxies, including our own Milky Way.
So it sounds like Einstein didn't just tweak Newton's ideas about gravity. He completely rewired our fundamental understanding of how the universe works. He moved gravity from being just a pull between objects within space-time to something woven directly into the very fabric of space and time itself. What does that really mean for how we even think about phenomena like black holes or the expansion of the universe?
It means absolutely everything for how we conceptualize these phenomena. This geometric viewpoint makes things like black holes, which are essentially extreme warps in the spacetime fabric, and the expansion of the universe itself, which is an expansion of spacetime, not just objects moving through space, conceptually possible and mathematically describable within a single coherent framework. It's not just a mathematical curiosity, it's the essential language we use to accurately model the universe on its very largest scales and understand the physics operating in the most extreme gravitational environments. It was a complete revolution in thought that fundamentally reshaped physics and cosmology.
Okay, so we've pieced together this incredible cosmic narrative from the tiniest quantum ripples in the first moments through inflation, the formation of matter, the first stars and galaxies, all guided by gravity, both Newton's approximation and Einstein's deeper reality. It feels like we've almost completed the puzzle, but then right at the turn of the 21st century came a discovery that threw us a massive curveball. A discovery that revealed that perhaps the vast majority, something like 95% of the universe when you include dark matter, is still a complete mystery. What was this astonishing find, and what does it tell us about how much we still don't know?
It truly was a monumental surprise, arguably one of the biggest in modern physics. For much of the 20th century, the prevailing question about the universe's expansion, ever since Hubble discovered it, was whether it would slow down and eventually halt, or perhaps even reverse and collapse, due to the mutual gravitational attraction of all the matter within it. We were trying to weigh the universe to figure this out. The stunning answer, delivered in 1998 by two independent teams of astronomers, was neither. By using type Ia supernovae, a specific type of stellar explosion that occurs when a white dwarf star exceeds a critical mass limit, resulting in a remarkably consistent peak brightness as standard candles to measure cosmic distances with unprecedented accuracy, they made a shocking discovery. They found that very distant supernovae were consistently dimmer, and therefore farther away than they should have been if the universe's expansion was decelerating due to gravity, as everyone expected. The only explanation was that the expansion of the universe is not slowing down. It is, in fact, accelerating. This discovery, which earned the leaders of the two teams the 2011 Nobel Prize in Physics, implies the existence of a mysterious, gravitationally repulsive component that permeates space and is actively pushing space-time apart, overcoming the pull of gravity on the largest scales. This unknown component was dubbed dark energy. Dark energy is now understood to be the dominant component of the cosmos, making up approximately 68% of its total mass energy content, more than dark matter and ordinary matter combined. Its defining characteristic is its negative pressure, which, according to general relativity, creates a repulsive gravitational effect, essentially acting like anti-gravity on cosmological scales. While its existence is strongly required by multiple lines of cosmological evidence, not just supernovae, but also the CMB and large-scale structure, its fundamental nature remains perhaps the biggest mystery in all of science. The two leading theoretical models are quite different. The first, and by far the simplest possibility, is that dark energy is the cosmological constant. This model proposes that dark energy is an intrinsic, constant energy density associated with the vacuum of space itself. It's uniform throughout space and, crucially, constant in time. Its energy density doesn't dilute as the universe expands. This idea actually dates back to Einstein himself, who initially introduced a cosmological constant into his equations of general relativity, though he later famously called it his biggest blunder, because he introduced it artificially to allow for a static universe model, which observations soon proved incorrect. However, in the modern context of an accelerating universe, a positive cosmological constant provides the simplest and currently best-fitting explanation for dark energy in most datasets. In stark contrast, alternative models propose that dark energy is not constant. These are broadly termed quintessence models. They typically propose that dark energy is associated with a dynamic, slowly evolving ultralight scalar field that permeates the universe, somewhat analogous to the inflaton field hypothesized to drive cosmic inflation. In this scenario, the strength and equation of state, the ratio of pressure to energy density of dark energy, could change over cosmic history, and it could potentially even vary spatially, leading to potentially observable consequences different from a simple cosmological constant.
And what's truly fascinating here, and maybe a bit unsettling for the simple picture, is that some recent research is starting to challenge this idea of a constant dark energy, isn't it? What are these new hints suggesting? Is lambda really constant?
That's right. For many years, virtually all observational data were consistent within the measurement uncertainties, with dark energy behaving exactly like a cosmological constant. However, recent and ongoing research, particularly from large-scale structure surveys, is beginning to provide tantalizing hints that this simple picture might be incomplete or even incorrect. Specifically, data from the Dark Energy Spectroscopic Instrument, DES, a major international collaboration currently mapping the 3D positions of tens of millions of galaxies and quasars over a huge volume of the universe to trace its expansion history with unprecedented precision, has provided initial results. These results, released in stages in 2024 and 2025 from the first few years of data, suggest that the influence of dark energy may not have been constant over cosmic time. The data hints, though not yet definitively, that dark energy might have been somewhat stronger in the past and could be weakening over time. Now, it's crucial to emphasize that this evidence has not yet reached the gold standard of statistical significance, often quoted as 5 sigma, required for a definitive discovery in particle physics and cosmology. More data and analysis are needed, but the implications are profound. If these hints are confirmed by future DESI data or other experiments, it would rule out the simple cosmological constant model. It would mean dark energy is dynamic, evolving. This would necessitate a major update to the standard model of cosmology, SDM. It could point towards a new dynamic form of energy like quintessence, or perhaps even require a modification to Einstein's theory of gravity itself on cosmological scales. It really hints that the universe might be far more complex and its fate less certain than we've perhaps comfortably assumed.
And if dark energy isn't constant, if it's evolving like these DSI results might be suggesting, that really shakes up our predictions for the universe's ultimate long-term fate, doesn't it?
Okay.
The endgame scenarios become much more varied.
It absolutely does. The nature and evolution of dark energy is the single most important factor determining the universe's ultimate fate billions and trillions of years from now. If dark energy is indeed a cosmological constant, as has been the standard assumption, then the current acceleration will continue indefinitely, perhaps forever. This leads to a scenario often called the Big Freeze, or heat death. In this future, galaxies beyond our local group will recede from one another at ever-increasing speeds, eventually accelerating beyond our cosmic event horizon, rendering them forever unobservable, leaving our local group isolated in an increasingly empty universe. Star formation will eventually cease as the interstellar gas reserves are exhausted. Existing stars will die out over trillions of years, leaving behind degenerate remnants like white dwarfs, neutron stars, and black holes. Over immense, almost unimaginable timescales, if protons are unstable as some grand unified theories predict, this leftover matter might decay into radiation. Finally, even the black holes themselves are predicted to evaporate via Hawking radiation. The universe would ultimately end as a cold, dark, featureless, and empty void, approaching a state of maximum entropy. A rather bleak outlook, perhaps. However, if dark energy evolves, as the DESI results tentatively hint might be the case, it opens up more dramatic and perhaps more interesting possibilities for the ultimate cosmic fate. If, as those initial DESI results suggest, dark energy is weakening over time, then the attractive force of gravity, from both ordinary and dark matter, could one day reassert its dominance on cosmic scales. The cosmic expansion could potentially slow down, halt, and then reverse, leading to a cosmic collapse where all matter and energy rushes back together into a final, fiery singularity, a scenario known as the Big Crunch. The latest evidence, while preliminary, has unexpectedly brought this scenario, which was thought highly unlikely for decades, back into the realm of serious scientific consideration. It would imply a cyclical universe might even be possible. Conversely, there's another theoretical possibility, though less favored by current data. If dark energy were some form of phantom energy, whose density actually increased over time, its repulsive force could become infinitely strong in a finite time. This could lead to a dramatic end known as the Big Rip. In this scenario, the accelerating expansion would become so violent that it would eventually overcome all other forces, tearing apart galaxy clusters, then galaxies themselves, then solar systems, stars, planets, and ultimately, perhaps even atoms and atomic nuclei themselves in the final moments. So you see, the journey from that initial singular point of infinite density to a cosmos filled with intricate structure, galaxies, stars, planets, and the potential for life is a story of breathtaking scale and complexity. The success of the Lambda CDM model in explaining so much of the universe's history and structure is truly one of the crowning achievements of modern science. Yet the very components that make the model work, dark matter and dark energy, which together constitute 95% of the universe's energy budget, remain profound mysteries. Their existence points not towards an end of the story, but rather towards vast, undiscovered frontiers of fundamental physics that lie ahead. Cosmology is a vibrant, ongoing field of inquiry, and the grand narrative of the universe is very much still being written, with potentially major plot twists still to come.
Wow, what an incredible ride that was. Zooming from the first fraction of a second through inflation, matter creation, structure formation, all the way to billions of years into the future and these possible cosmic endgames. It's truly mind-bending to think that the largest structures in the universe we see today, those filaments and clusters of the cosmic web are, in a very real way, just gigantic echoes of tiny quantum fluctuations from the universe's very first moments.
It really makes you consider the profound interconnectedness of scales in the universe, doesn't it? From the subatomic realm of quantum mechanics all the way up to the vastness of cosmological structures. And the fact that we're still grappling with the fundamental nature of 95% of our universe is dark matter and dark energy, well, it just means the biggest questions, the deepest mysteries are almost certainly yet to be answered. There's so much more to learn.
Absolutely. It's both humbling and exciting. So, as you, our listeners, go about your day, here's something to think about. If dark energy is indeed weakening, and those intriguing new DISI results suggest it might be, what would it actually feel like conceptually to live in a universe that's heading toward an eventual big crunch, where the cosmic expansion eventually reverses and everything starts coming back together? What new physics might we uncover? That's our ultimate cosmic fate, rather than the cold, empty big freeze. It's definitely something to mull over as you navigate your own corner of this ever-evolving and still deeply mysterious cosmos. Thank you so much for joining us for this deep dive today. Until next time, keep exploring.